Welcome back to the class. Today we will talk about ocean circulation. This is chapter 6 in your textbook, and we will follow the lecture slides here. There are two major types of ocean currents, surface currents and thermohaline currents. As the very name indicates, surface currents are the currents that occurs near the surface of ocean surface. And thermohaline currents, these are the currents that occur much deeper in the ocean. Between the surface current and thermohaline currents, surface currents are much faster compared to the thermohaline currents. And thermohaline currents occur below the pycnocline line. You might remember the term pycnocline. It is the depth in the ocean below which the density of the ocean water changes very quickly. So that line above the pycnocline, the depth of water above the pycnocline where the density remains constant, but below the pycnocline the density of the ocean water changes very rapidly. So first we will look at surface currents. What are the forces responsible for surface currents, and what are the components of surface currents? So the major driving force for surface currents is the wind which is blowing over the surface current. So we will borrow a lot of concept that we learned in the previous chapter of atmospheric circulation. These two chapters are very tightly linked together. Whatever we have learned in atmospheric circulation of wind, that will be very useful in this chapter. Surface currents are mostly driven by wind which are blowing on top of the surface of ocean. So that's what it says here. Wind is the primary force responsible for this surface current. 10% of the water in the world ocean is involved in surface currents. So it's only a very thin layer of the ocean on the near the surface which participate in the surface currents. The majority of the water in the deep ocean which are part of the thermohaline current. Gyre, it is a very distinct circulatory pattern that is observed in surface current. That's what is called gyre. It's current flow around the periphery of an ocean basin. So we have identified about 5 major ocean basin. So like North Atlantic Ocean, South Atlantic Ocean, North Pacific Ocean, South Pacific Ocean, Indian Ocean. So these are the ocean basin where we can find a very distinct pattern of this surface current circulation, and those those pattern of circulation of surface current is called as gyre. So here this is what it is showing. If you might remember from the previous chapter, there are two major winds, easterly winds or westerly wind. Here if we are looking at this North Atlantic Ocean, so this line in the middle, it represents equatorial line or equator, which splits the planet into hemispheres. So the northern hemisphere, you can see you have easterly wind and then you have a westerly wind. So when we are looking in the ocean, we are studying ocean here. So if we put ourselves in the middle of the ocean, so on your right it is east. So the easterly winds come from this eastern shoreline, and then you have this on your left, it is west. So it is your westerly wind that originates from this side. So we call it easterly and westerly. Westerly winds are relatively much stronger compared to the easterly, and these motion, and if you look on the southern hemisphere, it is exactly opposite. The easterly winds are moving left, the westerly winds are moving right, and the reason is because of the Coriolis effect, right? You might remember that the Coriolis effect makes things in the northern hemisphere and move a little bit to the right, and on the southern hemisphere it makes wind move to the left. So that is why you have these kind of circular pattern. Because of the Coriolis effect, there is this pattern, this rotation of ocean surface current, and that is strongly dependent on the nature of wind which is directly in contact with the surface currents. So here you can see two gyres here. This is your North Atlantic region, this is South Atlantic region. So this is your North Atlantic gyre, this is your South Atlantic gyre here. Now we can look more in detail about this North Atlantic gyre. You have these multiple different currents here. So on the east side, which is on the northeastern peak, northwestern peak of African continent, you have Canary current, and then if you come close to the equator, you have North Equatorial current, and as you get close to Mexican Caribbean island, you will see this Gulf Stream is originating here, and then it becomes Atlantic current, and the Atlantic current convert into Canary current, and the loop will complete here. So you have these different currents as a part of this North Atlantic gyre. So we are again just looking at this one gyre in the North Atlantic Ocean. Just once again, I will give you a sense of the direction, since we are looking at the ocean basin. So we are assuming that we are standing in the middle of the ocean. To the right of us it is eastern, to the left it is western side, and of course northern side, south is top and bottom. But I'm trying to give you a sense of direction, because if you go on the continent, this edge will become your eastern side, but when you are standing in the North Atlantic Ocean, this edge or coastline is your west. So that is a little bit confusion, but try to understand this reference of direction where you are standing. So that direction, east, west, north, south, it changes relative to where you are standing, whether you are on the continent or whether you are in the ocean. So these are the different components of gyres, or different currents in the gyre. And one thing you might notice that near the equator, the currents are almost straight line going from east to west, and that's because Coriolis effect is almost negligible near the equator. But as you start moving northwards towards the pole, the Coriolis effect starts to become dominant or stronger. So that's why the Gulf Stream is your warm water. It is taking higher temperature from the equator region to the polar region, to the northern region. So that is another important aspect of this different currents in this gyre. So the currents in the northern hemisphere, if you look at these, the North Equatorial current, these are the currents around the equator, and as we learned in the last chapter, equator is the area on our planet that receives majority of the solar energy, or it is the hot strip on our globe. So the wind that is blowing around here, it's also relatively warm, and that makes the ocean water also relatively warm. So this wind, as it is driving this current, North Equatorial current, this current will come across some of these boundaries, continental boundaries, and so it will turn around here, and then it will continue to go northwards, and that is where you will see now its direction will start to change because of the Coriolis effect. It would have continued in this orange arrow direction. Had there been no Coriolis effect, then it would have continued in this way. But since due to the presence of the Coriolis effect, these direction will curve and it will change in this circular pattern. So that is how the Coriolis effect is a strong influence that determine the direction how this gyre will rotate. And it is exactly opposite. Right now you can see this North Atlantic gyre, it is clockwise, right? So it is clockwise, but if you go in the South Atlantic basin, you will find that the same South Atlantic gyre will become counterclockwise, because we know that the Coriolis effect moves the air to the left in the South Atlantic Ocean. So this is again surface current flows around the periphery of ocean basins. So these ocean basins, the surface current is just moving around, and it comes in contact with the shoreline of these different continents, and that is also responsible for the change in the direction of this current. But the majority impact that defines the direction is coming from the Coriolis effect. There is another very important term here, Ekman spiral. It is based or it is named after the scientist who first proposed this concept of Ekman spiral, or the spiral way in which the water rotates in the ocean. So if you look at this, near the surface you have wind force in this direction, but the water is actually moving in this another direction, and that is again due to the presence of this Coriolis effect. The direction of the current changes a little bit to the right in the northern hemisphere due to the presence of Coriolis effect. But if you think about this effect and the wind is primarily moving the water in the top layer, which is directly in contact with the wind force. But if you think about the layer of ocean water which is underneath, as you go deeper and deeper in the ocean, the effect of wind force starts to decrease on this deeper layer in the ocean, and that's where the effect of Coriolis effect will be more dominant compared to the wind force. And that's why this is not exactly, the different layers of oceans are not moving exactly in the same direction. In fact, if you go deeper in the ocean, you will find that the water is moving exactly in the opposite direction to the wind force, and that is because the wind force become very weak. The effect of wind force become very weak, and the Coriolis effect is very dominant here in the deeper layer. But as you look at the surface, they are relatively the Coriolis force and the wind force are relatively about not have the same effect, but they can counteract each other, and so that's how you have this direction. And this is called as Ekman effect, that how you have these different direction at different depth of ocean for the surface currents, and this actually creates a kind of a spiral kind of a movement where the water is moving in a spiral shape in this whole gyre. And Ekman transport, it explains the net movement of water in surface currents, because if you think about this again, on the top surface the water is moving in this direction, but as you go deeper in the ocean, the water is circulating in the exactly opposite direction. So this will kind of counteract the deeper ocean circulation. It's still not the deep ocean, it is still near the surface, but compared to the surface it is little bit the underneath layer. It is moving the water in a different direction, and so why the net transport of the water due to surface current will be not exactly same as the water which is moved by the wind forces, because if you look deeper in the layer, this layer is moving water in the opposite direction. So that's why there is a term Ekman transport that explains the net movement of water in surface currents. This is again the same idea trying to explain here. You have trend wind, it is moving in this direction, but you have actual water moving in this direction because of the Coriolis effect. And if there was no Coriolis effect, then the water would have been moving exactly 90 degrees to the wind direction. This is a very important concept here, that why water is turning like this near the equator. So if you look at this depth of water, there is a mounding of water near the North Atlantic region. So this is a color map showing the depth of water or the height of water at different location in North Atlantic Ocean. So the red color indicates higher height of water in the ocean, and this yellow color represents lower and the green color represents even lower height of water. But this mounding of water is not very significant compared to the entire width of this basin, which is about thousands of miles, around 6,000 miles width of this basin, and this mounting is about only 10 feet, so that is negligible compared to the entire thickness or entire width of this ocean basin. But even that small mounding of water will propel these surface currents to go around it because of this pressure effect. It cannot go over it because of higher pressure in this region. So what will happen, all this surface current, they will just go around it, and that's why you have this kind of a oval gyre shape due to the Coriolis effect, due to the pressure gradient, due to the friction offered by these continental boundaries. So these are the different forces acting here. One is gravity or the pressure difference, another is Coriolis effect, third is friction due to the continental boundaries. And this also, this water mounding, what it will do is it will kind of lower the pycnocline as well here, because now you have lot more ocean water here, and that is kind of push the pycnocline little bit downwards, and also the thermocline. So that is another impact here. So these are your 5 major gyres here. This is North Pacific, South Pacific, in the Pacific Ocean, and again this is in the northern hemisphere, so we call it North Pacific. This one is in southern hemisphere, so we call it South Pacific. And you can look at the direction here. In the northern hemisphere, all the gyres are always clockwise in direction, they are moving. But in the southern hemisphere, the gyres are counterclockwise moving, and that's because of the Coriolis effect, because the Coriolis effect will move the wind towards right in the northern hemisphere, and it will move the wind towards left in the southern hemisphere. And in the Indian Ocean, again here it is, you can see it is counterclockwise because it is in the southern hemisphere of our planet. And there is a 6th gyre which is in the Antarctica. This is our 6th gyre, and this is mostly confined in the Antarctica region. But this water which is in the southern hemisphere, it comes in contact with this gyre in the Antarctica, and that helps move lots of these cold wind or exchange the heat from the equator to the Antarctica region. This is again the description or the color mapping of gyres in different oceans. So first we will look at northern hemisphere. Here this is your northern Pacific, and this is southern Pacific. Again, the direction of the gyre here, it is a clockwise direction. The red color represents the warmer air or the warmer water in the ocean. So near this is the equator, it is all warm water. This becomes Kuroshio current, and then it continue to go upwards, northern part, and as it descends now it will bring this cold water from the polar region, and that is how you have these cold environment or cold weather in the California region, because of this descending cold water from the polar region. But if you look at this in the Washington area, this warm water from the equator, it rises up and it goes it brings this warmer environment or warmer weather in this region. So even though they are at the same latitude, but they have a different weather condition. On the east coast, because of this Gulf Stream which is bringing lots of warm air from the equator, and that's why you have this warm and humid environment on the east coast. But if you look at the west coast of continental US, you have this cold water sinking down from the polar region toward the equator, and that influences the weather on the west coast. So just remember, this is one example that how these gyres controls or affect the weather that we see in different part of the world. Even at the same latitude, we can see different atmosphere or different weather. And now look at this southern hemisphere. You have again the wind, the warmer air moving around here in the counterclockwise direction, but as it comes near the Antarctica region, it starts pulling cold water, and they start coming up here, and that's how this southern South America continent sees this cold weather here. But if you look at the eastern coast of South America, because of this descending warm air from this counterclockwise direction, this Brazilian current is bringing hot, humid air from the equator side. So you have a different, actually exactly opposite weather on the east and west coast of South American continent. This is a similar pattern that you will see here in the Indian Ocean. You have warm air going counterclockwise, pulling heat and warm air from the equator towards the polar or Antarctica region, and then it is bringing up this cold air, and that is how you have these different weather here in the Australia. You can see this on the east and west coast. They are both warm environment because of these warm air going around here like this. So these are some of the names of the currents. Western boundary currents, fast. So another important factor that I want to mention here, the western boundary and the eastern boundary current. So again, just remember this sense of direction here. We are looking at the ocean basin. So this part here, this California current, it is considered as the eastern current, and this one is Kuroshio current, is considered as a western current. This is a transverse current, the north equatorial current, because it is going straight from east to west. And this one is North Pacific current. This is also considered as a transverse current. But this Kuroshio current, California current, the California current is considered as the eastern, and this Kuroshio current is considered as a westerly current. And there is a difference between easterly current and the westerly boundary current. So since they are near the continental boundary, those are also called as boundary currents, and if they are on the eastern side, they are called as eastern boundary current, and if they are on the western boundary, they are called as western boundary currents. The western boundary currents are faster, they are narrower, but they have a very well defined boundary in which they run, and they are much deeper compared to the eastern current. Again, just remember this is a very important distinction, and that is responsible for the weather condition, and that is also responsible for the survival of different organisms, plant as well as animals who exist in ocean environment or marine environment, because different water will have different ability to support life in ocean. Like warmer water are nutrition depleted, they don't have much nutrition, but the cooler water has lot more nutrition compared to the warmer water. So wherever you will see these blue lines, there is more chances of marine life, and the fish life will be lot more dominant there. Because these water, the blue line, the cooler water, are a lot more rich in nutrients to support marine life. So these are the major differences. The western boundary currents are faster in their velocity, they are narrower, and they go much deeper in the ocean, whereas the easterly boundary currents are relatively slower in their movement. They are wider, and they are not very well defined in their boundaries. So they are pretty wide in their channel, and they are relatively shallow compared to the western boundary currents. and also the eastern boundary currents are relatively nutrient rich, so they will support a lot more life. But this is all about the northern and southern gyres here. So this is what it is explained here. Western boundary currents, those are faster, those are deeper, and the current that move warm water poleward in each of the gyres. These are some of the example. I want you guys to remember some of them. The Gulf Stream is one example. In the Atlantic Ocean, Japan Kuroshio current, we saw that. In the Pacific Ocean, Brazil current. It is in the southern hemisphere, and this one Eastern Australian current. So just the name indicate, but it is little bit contradictory here. It is showing it is a western boundary current, but its name is Eastern Australian current. So I'll just quickly make it clear here. If you look at this map here, so Eastern Australian current, because it runs along the eastern coast of the Australia, that is why it is called as Eastern Australian current. But it is a westerly boundary current, because if you look at the ocean basin, it is on the west side of the ocean, but since it runs along the eastern coast of Australia, it is called as East Australian current. On the other side, if you look on the west coast, this is a easterly current, because if you look into this ocean basin, this is a east side of the basin, but it runs along, this current runs along the west coast of Australia, so it is called as West Australian current. So just remember this difference. It is name is Eastern Australian current, but it is actually a western boundary current. Some of the example of eastern boundary currents: Canary current, Benguela current, California current, West Australian current, Peru current. Eastern currents are shallow, opposite to the western current. It is much wider or broad with ill-defined boundaries. But another important thing is that it is nutrient rich and it carry cold water toward the equator. This is showing here the volume of water carried by surface winds in different part of the ocean, and there is a term here for this number. It's called word drop. So these numbers represents how many million cubic meter per second the water is carried by the current. So million cubic meter per second. So million cubic meters volume of water every second is moved by these currents. So you can imagine, so like I mentioned before, the westerly currents are relatively faster compared to the easterly currents, and these number represents the rate of movement of those volume of water per second in different gyres, in different part of the gyres. So the easterly gyres or the easterly currents in this gyre, they carry less water compared to the westerly currents in the gyre. So these number represents how much water is carried by different current in this gyre, and there is a term here which is called as word drop, and this term word drop comes from or coined in the honor of the scientist, a Swedish scientist who first developed this concept or this idea of the volume of water carried by surface currents. Transverse current that flowing from east to west and west to east, like eastern and western boundary currents. I gave you the example here earlier, like this North Equatorial current and North Pacific current. So those are the example. Westward flow of transverse currents near equator unimpeded for greater distance. So if you look at the westward current flow, this is relatively unimpeded, there is no disturbance here. But if you look at the eastward, there is more boundaries here, so it is not it kind of get disturbed in its way. So this is what it is. This is here showing the effect of Coriolis effect, that how the water changes its core in the gyre. So if there was no Coriolis effect, this will be a perfect circular rotation, a very symmetrical movement of these different currents in a gyre. But due to the presence of this Coriolis effect, and as we move northwards from equator, that effect, Coriolis effects, become more dominant. So these lines will start to bend earlier, and it's kind of a cross circuit, the whole this effect here that you see. And also the center of the mass of this circulation current, it shifts westward because of this rotation, this Coriolis effect. It moves the center of mass of this circulation pattern westwards. Gyres consist of currents that blend into one another. Flow is continuous. It's a balance of wind energy, friction coming from the boundary, continental boundary, and the Coriolis effect, and the pressure gradient propels gyres and holds them along the edges of ocean basins.